and later on we will give the floor to everyone to ask questions and discussion. And hello everyone, good morning, good afternoon, and good evening. And I guess nobody's here at midnight, so we're good on that one. Welcome to CRISiSLab webinar. So this is the last one in 2021. We're excited to have Dr. Benedikt Halldórsson here to give us a presentation. I'm Alicia Tsui, a research officer at Joint Center for Disaster Research at Massey University in Wellington, New Zealand. To those who newly joined us today, welcome you. So as part of an earthquake early warning project in New Zealand to explore the concept of community-based EEW using low-cost sensors, we host regular webinar sessions inviting key speakers around the world for our community practice. So this is another year we all had some challenges and progress, and glad to see you all here. And we'd like to thank you all for the support. As a last webinar, we are very happy to have Dr. Benedikt Halldórsson from the University of Iceland to give us a presentation on his thoughts on earthquake early warning and operational earthquake forecasting in Southwest Iceland. Okay, so let's give it the floor to Dr. Benedikt Halldórsson. I will just stop sharing the screen.
Hello, everybody. Good to see you all, and thank you for tuning in to the webinar. Let me share my screen here. That's okay. So I assume everyone can see this photo of the eruption that was happening here earlier this year. This was a very exciting time in Iceland. Actually, the last 2 years have been rather exciting in terms of earthquakes. It's been teaching us a lot about how little we know about nature, and it keeps us humble, which is the right state of mind to be in. But right, so as Alicia said, I come to you with, as a geophysicist and an earthquake engineer and engineering seismologist, all of those things in my education and practical experience with my thoughts on early warning here in Iceland and what we have been doing in terms of operational earthquake forecasting and what that means. Now, my affiliation is with the University of Iceland and the Icelandic Meteorological Office. These are the two major research and monitoring agencies here in Iceland, and I'm lucky to have my feet in both places. Now, I want to state from the outset that the work that I'm presenting here is a mixture of results from a fruitful collaboration with multiple people, colleagues and friends in European and domestic research projects. But I'd like to take the opportunity to actually acknowledge Hamish, because it all started with us meeting in Geneva a few years ago, where a nice startup, a New Zealand startup, was eager for input into their new product, the CUSP instruments. And they had excellent instruments. It was never a doubt in my mind that I wanted to work with someone that was starting up at a new product, because their minds are so open. And I thought the collaboration of Hamish and I was amazing. And in fact, the first CUSP instruments that came to Iceland that I deployed in an urban array, small aperture array here, and the two of them are shown here here next to an earthquake fault that Hamish has actually visited. That's where it started. And for a while, until the Canterbury earthquake of 2010, the earthquake here in Iceland in 2008, a magnitude 6.3, had the largest ground motions on record on CUSP instruments. So the New Zealand connection is alive and well, and it was really the start of it all. But as an overview, I'll talk about a recent project or a current project that I'm involved in here, the Turnkey project, and its focus. Then I will shift to a very localized situation here, the tectonics here in Iceland, because if we are going to be trying to do anything in terms of earthquake early warning or operational earthquake forecasting, we need to really understand what is the animal that we're dealing with here, the nature. Then I'll talk about the instrumentation using the Raspberry Pis in Southwest Iceland and how they are the elements that make earthquake early warning really possible here. And then I'll look critically at it. And then I'll talk about this vague idea of earthquake forecasting, of aftershocks and main shocks, and then, okay, so what is it that I personally feel from my experience are the important things. So, okay, the Turnkey project, it's a European project. It's an H2020 project that the European Commission was calling for. They wanted a project that was addressing earthquake early warning and operation and going towards operational earthquake forecasting. Now, these two concepts, you are probably much better versed in earthquake early warning than I am, but we are looking at this limited time interval after the earthquake until the damaging waves hit our infrastructure. Do we have enough time? And if so, do we have any decision support systems in place that allow us to take efficient decisions that mitigate the risk due to the waves that are on the way? Now, this is what we said we would do in this project. We would investigate the feasibility of it. Now, the other project, since we are a bunch of engineers, when we looked at the operational earthquake forecasting, this is a very vague idea for us, and we, as very practical people, we kind of had a tendency to focus on what we could actually control, what is inside our control sphere. And that was basically the response to earthquakes. Basically, when the earthquakes waves are hitting and what happens afterwards is what we wanted to optimize in real time. The quantitative estimates of the shaking and its peculiarities, damage, likelihood, and the risk in real time. But so we're going from here down to here to earthquake early warning, and then at least into earthquake operational earthquake forecasting. So, and there's another sister project going on called the RISE, and that one is populated with a much higher proportion of geophysicists, and they are focusing more on the operational earthquake forecasting. So these two projects, they actually contribute to one another and build up the weaknesses of the other. But the Turnkey idea, or the Turnkey approach, is actually demonstrated in 6 European testbeds. It is in the capital region of Bucharest. It is in the Pyrenees in France. It's in the seismic zones of Iceland, also in the Gulf of Corinth in Greece, a very critical infrastructure hub in southern Italy, and then a geothermal field in Netherlands that is subject to man-made earthquakes. Now, all these test beds, they together cover a wide range of existing sensor networks and hazard levels and what have you. So throughout looking at these test beds, we want to get experiences from all these test beds and real-time data that feeds into the network or the common testing of a turnkey platform that is supposed to take to have an early warning module, operational earthquake forecasting module, shake maps of all types, exposure database, enabling real-time loss estimation, etc. So this is what we are going towards, and this project will be finished next year. Now, the basic concept of early warning is something that you are undoubtedly very well familiar with, and I will not go into that here. I will be going into the basis for the basis. But there are multiple algorithms in place worldwide, either in operation or being tested. And they differ, and the comparison of them is not a straightforward thing. But we know that the concept of early warning has been comprehensively proven for these big earthquake faults. Now, but the Turnkey project was going to look at how about the seismic regions in Europe? And this is one of the deliverables of the Turnkey project. And of all I can say about the Turnkey project, I think that the YouTube channel, if you Google or if you just go on YouTube and search for Turnkey earthquake, then a particular good overview in terms of our approach, which is the latest research that we've done in this field, coming from all angles, is a compilation of the presentations that we gave during the special session of the ESC, European Seismological Commission conference in September. And there's a playlist for it. And then I think the other project, RISE, also has these videos. So there you can select your video and really get better feedback, and which includes, for example, something like this. Now going to Iceland. So quickly, Iceland is located up here. It is notably the only big landmass that is above water along the entire mid-Atlantic ridge, which is the plate margin here in the north between the Eurasian and the North American plates. The reason why this part is above sea level is because there is a mantle plume underneath Iceland that basically elevates the crust on a large scale. The center of the mantle plume is about here. It's about 200 to 300 kilometer wide, very slow uprising of mantle material. But it is stationary compared to the crustal plates. The crustal plates are moving actually to the northwest, and what they do, the mantle plume, it pulls the mid-Atlantic ridge repeatedly over to its location. And the current situation is that the tectonic plate margin is along the red line here as it approaches Iceland, and then continues here. But on land, it is shifted towards the east. And that forms two transform zones in the north and the south. And I'll come back to that. But needless to say, the mantle plume dominates the volcanic activity of Iceland, while the plate spreading is dominating the tectonic earthquakes. But there's a complex interplay there. Now, if the transform zones are in the south and the north, then where's the population? Well, the population is primarily down here in the south, in this transform zone here. Nobody lives in the highlands or on the volcanic zones, really. And the transform zone up north is quite, it's offshore. So it is here that we see the largest seismic risk. And so this is the area that we focus on, because that's where the infrastructure is. Now we need to mitigate the risk in this area, and that is what I'll be focusing on here. Now, as a result, the hazard map for Iceland, the official one, looks like this, indicating the highest probability of exceedance in peak ground acceleration off the coast, on the coast, and off the coast of North Iceland, and here in the transform zones of South Iceland. Now, this is probably 10, 20 years old and was developed using simplistic uncertainty and seismic activity measures and earthquake sources. Now, it's very important that we deal with this in a very, let's say, physics-based manner, and that harkens back to the earthquake early warning concept. Now, what we're doing now is we are focusing on these two boxes, the northern fracture zone and the southern fracture zone, but I'll be focusing on the southern one. And here we can see that the catalog of Iceland shows that the largest earthquakes happen in these transform zones. And we need this information to move towards physics-based hazard assessment. What enables that is the very dense monitoring network of multi-system monitoring of multiple geophysical markers that is needed for us to get an overview of what the fast tectonic movements, like in earthquakes, and the slow tectonic movements, the plate motions, how they operate. Are they exposing areas where we have a seismic slip, for example? And this, the network shown was from the Icelandic Meteorological Office. Now, focusing on this southern belt here, the North American plate is here and the Eurasian plate is here. That the plate margin is along this transform zone here. And in most other places where you have the vectors of tectonic motions, they are parallel. There forms a long strike slip fault. In this case, we would expect a sinistral or left lateral strike slip fault from about here to here, about 130 kilometers long. And it's clear that the seismic potential of such a fault is massive. However, the peculiarity is that instead of a long fault, we get an array of north-south, parallel, near vertical strike slip fault, right lateral strike slip fault. And on those faults is the tectonic strain released. Now notice that these faults are all much shorter than what one would be across this entire zone. So that has massive implications for the earthquake early warning and also for the seismic hazard. Now, we have now started modeling this, modeling the seismic, let's say the variation of seismic potential changes drastically from the eastern part over to the western part, going from about 7 maximum size earthquakes to about 5.5. Now, granted, these are not the large earthquakes not that large earthquakes, but these are the largest ones that we have. You get much larger earthquakes even close to you. Not talking about the big one, the big faults. So, but it's relative problems that we all have. So this is what we here need to focus on if we are going to make any sense of this and evaluate if an early warning system is feasible or practically feasible, and how we can evaluate the hazard better. So we have created a 3-dimensional fault model of this zone, and where we have multiple instances of it, all complete with data files that enable dynamic or kinematic rupture modeling and allow for physics-based modeling of earthquake rupture and the corresponding ground motions. Now, this model has seismic activity that is consistent and it's calibrated to the plate motions. And it completely explains the earthquake catalog. So simulations using this model will actually be equivalent to to a seismic hazard assessment based on physics. Now I'll skip North Iceland. And as I said, this new 3D fault system, it explains the earthquake catalog, the black and gray area is the median and the 16th to 84th percentiles of the seismicity predicted by the 3D model. And this came out with us never considering the earthquake catalog. We just started from first principles. And when we compared with the catalog, everything was consistent. So we trust this model, and we have converted the 3D fault system model into an equivalent model that is suitable for conventional PSHA. And we have shared those results with the project in Europe that is responsible for harmonized hazard assessment across Europe. And now finally, the results are actually looking like something that we relate to, and that was not the case. It was always wrong for Iceland when the Europeans where other Europeans were trying to evaluate it here. Now, so this is a massive input consideration for hazard assessment. And so we have approached it from physics. Another massive input assumption in hazard assessment are the ground motion models. These ground motion models here is the PGA versus the distance of several models and 3 magnitudes compared against the Icelandic data set, the diamonds. And these ground motion models are what were suggested in the last European efforts that should be applicable to Iceland. Now, the case is this. In Iceland, for a given distance, we get much lower ground motions far away from the fault than in other regions, than if we were using empirical attenuation relationship from other regions. But if we are closer to the source, we get much higher peak ground accelerations than is known in other regions. So very high near fault accelerations, but extremely fast attenuation with distance, and the high stress drop in earthquake sources in Iceland makes for short durations. So we have generated suites of new ground motion models to use in Iceland, and they are unique. The only region worldwide that comes close to this kind of attenuation are a couple of sub-regions in Italy. So now, with this in mind, what about earthquake early warning? Okay, in the turnkey project, we deployed 50 Raspberry Shake 4D accelerometers in the blue points that you see. Hamish, I was not quitting on any arrays, so I set up 3 new ones here in this zone, because we were using the opportunity because there was a volcanic eruption happening here and a lot of seismicity. So we were kind of surrounding it with instruments, and that was an opportunity. We also have 6 continuous GPS instruments that actually plug into the Raspberry Shake because of a new system in the new operating system in the shakes that I will talk about. Now, so when we not only installed these Raspberry Shakes at new locations, but also co-located them with stations of the seismic network, because until now, the National Seismic Network had the inability to record the entire seismic wave field of strong earthquakes in Iceland. And therefore, its duty is to monitor the hazard, and it was not really doing it. But now that is in place. What's more, everything operates in real time. So now we actually have an earthquake early warning infrastructure in place, because the algorithm is operating on the server and the instruments are there. Now but by introducing these these instruments along the spine of the transform zone, we have essentially completed the near-fault seismic and volcanic observatory of Southwest Iceland. And so with that in place, here are some examples of the installations. Basically, all of them are on 4G wireless telecommunications, either free field outside or inside, some with GPS, some not, and a few for structural monitoring. But it's important to notice that the Raspberry Shakes were originally optimized for earthquake early warning, but now they have a particular module called the CAPS module, Common Acquisition Protocol Server, that allows the streaming of multi-format data. So now it is the Raspberry Shakes that we have are multi-sensor units that act like a connection hub for other instruments to connect to, and uses a single communication model that compresses the data and transmits in a consistent data format. Now, the system in place has this flow chart associated with it. Everything works around the CAPS, the compression module. The SeisCom system that you may be familiar with is run alongside the Presto algorithm, which has been implemented. And so the data is delivered to the system with minimum latency through the wireless communications that we have found are quite stable. And we've tested multiple IoT and LTE-M types. And with the CAPS system compressing the data about a factor of 5, it really gives us increased bandwidth that we can, that increases the reliability of our connections. So, excuse me. Now, finally, the QuakeLink module, it integrates the solutions from the SeisCom and Presto and proactively forwards event and station parametric data to the engine of the turnkey platform for post-processing and use in future prediction of shake maps and losses. Now, okay, so next one. Next. Excuse me. So we took we had the opportunity because during our installation, or just after we installed the instruments, a massive seismic sequence happened. Maybe that sounds familiar to Hamish. Because when we installed his instruments in South Iceland, 7 months later, we got the magnitude 6.3. Don't tell anybody, but I'm not allowed to set up any more instruments. Okay, so this seismicity was happening while and was recorded by the network. This is the reported seismicity from the start of the sequence until the eruption started. And it's quite complicated pattern here. But it culminated in a volcanic eruption on 19th of March, and it lasted for six months. But what happened here is that the earthquake started up here with a magnitude 5.7, a transform fault, north-south transform fault. And after that, the seismicity was migrating towards the southwest, which is the predominant strike direction of volcanic fissures, meaning that tectonic extension associated with volcanism happens on these northeast-southwest faults by normal faulting. But on top of that, we had transform faulting. And during this period, we had 7 earthquakes, strike slip earthquakes all along this dike that essentially opened up the pathway for or released the stress, the lock, so that the magma could come up. And so when the eruption started, which is about here, that's when the seismicity died down. But we recorded this well and are still recording it, and we really got a good test of what the system can do. I'm quite happy with it. And this is just about the compression. Now, here is a playback of as a magnitude 5.4 down here. And this shows the traces coming in real time in this playback into the system. The red triangles light up when the P wave passes. The S wave is passing here in the blue. And the location is improved the more phases get in. This is the approximate location of the earthquake, as does the event magnitude. And so this is how the system operates in real time with very little delay. And what we see is that here is this chart is plotted versus time from the source time. And for a magnitude 5.4 event, the blue line shows the increased number of phases coming in as stations record the motions. And the red shows the magnitude determination. And it is clear here, if we generally assume that a magnitude uncertainty is about 0.2, the only 3 to 5 seconds after the earthquake, we have a usable magnitude, which is within the uncertainty range, and also for a much smaller aftershock. Now, so the system is there and it works and it has a very low latency, and we are quite happy with it. It has been very stable. We took very good care of outfitting the stations with good components to protect our investment and increase the reliability of the system. But if we now take a step back, okay, so we installed the stations. We have ensured that the system will not saturate. The national system will not saturate when there's a larger earthquake. Moreover, we have everything in place for an earthquake early warning. We need to ask ourselves, are we doing it for us or are we doing it for others? So we need to talk to the stakeholders, and this is what we did from the outset of the project. So we know it works. We've shown that it works. The stakeholders, they are interested in it. They may need it, but it's not clear if our efforts are actually going to be that useful to the stakeholders. That depends on their needs, the types of operations, the infrastructures, and the relative locations of their infrastructure to the seismic source zone. Now, this changes for every stakeholder. So we started a turnkey project to talk to stakeholders and ask them, if we imagine such a system in place, would it be useful to you? And that really started a conversation that I think sometimes it was not very easy, but in the end, I feel that it really helped to understand better the point of view of the stakeholder, and hopefully it helped them to understand our point of view. But our purpose is the mitigation of risk. So we need to ask the stakeholders, this system is here, is it useful to you? So what we can do as seismologists is to actually carry out simulations. Now, this to actually show that it works in practice, but also theoretically. So what I plotted here is the maximum considered earthquake of a 5.5 in this part, in the western part of the transform zone. And I plotted here the ground motion amplitudes. You see here the yellow one, it goes to about 2.5 meters per second square. It's about 25% G. The maximum here for 5.5 in the near fault region, and beyond about, let's say, 10 kilometers away from the fault, then the motions have dropped below 10% G. And so But these contours here are effectively the S wave propagation contours. So if we think about, if within 5 seconds of the, let's say, if the system can determine in 5 seconds what's going on, then at that time, the S waves are here. So everyone inside this innermost circle, an earthquake early warning is of no use to them. But for everyone outside it, it is useful, we think. But no, it's not. Because outside these 5 seconds, the ground motions have died down so that they no longer pose a threat to the infrastructure. Now, in the next zone, a magnitude 6 earthquake can take place. Same situation. Now, the maximum concentrated earthquakes increase towards the east. So now we see that the ground motions, they have some amplitudes, about 20% G for a magnitude 6.7 here. And so probably around 25% G values outside the 5-second circle. So effectively, it is only the people inside this zone between 5 and 10 seconds of the S waves where the intersection of strong motion amplitudes and an alert can actually be combined and shown to be actual in the moment. But beyond that, there are no significant ground motions to consider. So earthquake early warning is then effectively here, in this case, only useful for a very narrow spatial area. So what do we then do with this information? The long-term forecasting of earthquakes, the hazard maps. Basically, the earthquake codes, building codes, they are the ones that can protect us, the infrastructure, over time. And we don't need to rely on transient alerts. So if we focus on that, we need to, if we give ourselves that in Iceland, because of the fault system geometry and the maximum size earthquakes, we can barely show that earthquake early warning is practically useful. So what we do now is we are more than ever confirmed in our opinion of just going towards physics-based long-term PSHA assessment that also uses stakeholder-specific deterministic seismic hazard assessment, high-frequency motions and comparison with empirical models. Yeah, something like this, simulations of actual maximum case scenarios. Handling of uncertainty better and conveying that uncertainty to the stakeholders. But for the future, we need to, if we are going to make any progress, we need to start monitoring multiple geophysical markers, seismicity, tremors, deformation, water levels, gases, VP-VS ratios in a single system and try to learn from transient, near simultaneous abnormalities in multiple geophysical markers simultaneously. And with that, I would like to thank you. I think I went over time, but if you have any questions, I would be very happy to answer.
No worries. I think that was a really great presentation, Benedikt. Thanks so much for your presentation. I'll give people some time to put in their questions in the chat box, or if you have any burning questions, just feel free to raise your hand virtually. But I really enjoyed your presentation, and I think one of the things that I quite impressed how you were able to use low-cost sensors and actually show us that it works, but also the question about, does this actually mitigate risk, and how useful will it be for stakeholders? I think those are important questions to ask. And thanks for showing us how it's applied in your context in Iceland. And it's pretty impressive. I guess I'll just go straight to the first question, because somewhere in your presentation that you mentioned that the algorithm is operating at the server. So one question from Raj is, most of the processing for earthquake early warning system happens at the central location. Do you see any opportunities in using processing at the node level, let's say the sensors?
Yeah, that's a good point. I don't. And the reason why is I would have needed to see how should we say it? I would have needed to see a massive intersection of large ground motions inside the area where lead times are significant, because that would then have...
Actually, the bit you just missed is hilarious, because Raj is saying, oh, what about using local...
Is that
sorry,
question?
Bill? Was it yeah?
Yeah, I thought he was asking. Anyway, so yeah, this is my go-to. This is a simple simulation, but just a thought experiment with the fault system here in Iceland, and the propagation time and the amplitudes gave the same result. Let me say this, to go into single station or on the node level to really start to optimize the earthquake early warning, then what I would have liked to see then is if we had a fault system like this, so we get an epicenter or hypocenter here and a rupture causing a 7.5 earthquake or something like that past here, with a capital region here and multiple towns along the way with geothermal and hydroelectric power plants in the way as well, then the zone of forward directivity pulses is effectively coming here from this part of the fault here. This part of the fault would be then pushing the near fault pulses into the city. So that would have, if we had this kind of a situation in the tectonic system, that would have completely changed the picture. And yes, then I would definitely have considered going into higher optimization of using these instruments on a node level to get, let's say, faster or improved information.
Thank you. I guess one point of clarification, another question from Chantujan, because you didn't go into the algorithm level, but just I guess a clarification how you detect earthquakes for your earthquake warning approach. Do you use P waves as a technique, or maybe just a brief overview of the algorithm?
So the Seiscom system and Presto, they work hand in hand. The Seiscom picker monitors and detects the incoming phases and the amplitudes, and the ScanLock module there locates the event. Now, at the same time, the Presto system that was an outside incorporation into the system works separately. I don't have detailed information on exactly how the phase pickers, how they work. But one of the things that we need to do is to allow fewer stations that record P phases to allow the algorithm to start calculating the approximate magnitude and location based on fewer phases. Right now, it is limited at 6 phases. 6 P phases need to come in before anything is done. And that's just too much. We can do much more with fewer stations.
Thank you. So we have a question from Caroline. Who are your stakeholders for earthquake early warning in Iceland?
I don't think we really have any, because those stakeholders, because of what I showed, there is very little intersection of considerable ground motions that are expected to come after the alert is theoretically possible or practically possible to be delivered. The civil, also one thing, civil protection here is responsible by law to issue, let's say, alerts, orange alert or red alert. And the way they look at it is from completely the other end. They really like what we're trying to do in terms of, in terms of the let's say, earthquake early warning and trying to move the needle in that regards. But in the end, and this is one phrase that I heard, is that if you know that there's an earthquake waves on the way and you call me, it's always going to be at least a 30-second phone call. So unless we have a decision support, automatic decision support system in place that can eliminate this, then we simply go about, let's say, go about our business, trusting in the building codes, the strong building codes, and the fact that despite the magnitude 6.3, 4, 5 earthquakes here in the past 20 years, and multiple buildings in the near fault region that were designed for acceleration levels much lower than that actually happened, there were no collapses because our infrastructure, our building exposure, let's say, our buildings are built in such a way that gives them residual strength against earthquakes. It just so happens. So we're fortunate there. So they don't see, the civil protection doesn't see, and other stakeholders, they don't see the need. And as an earthquake engineer, this is a very important conclusion for me, because as a scientist, as an engineer, I want to quantitatively estimate if it is feasible or not. I don't have any I don't invest in what the outcome is. I just want it to be clear.
Yes, it's quite good to see different perspectives on the use of earthquake early warning, and also to see from the perspective of civil protection, but also from scientists. So thanks for those insights. So we have a question from Martha asking about the South Iceland seismic zone. Are you sure that there's no true going long fault at the depth under the South Island seismic zone?
It is clear that at depth, that's where the plate margin is definitely from east to west, and we see it in deeper earthquakes, but over the instrumental catalog here in South Iceland from 91, we have mapped subsurface seismic sequences we're using relative relocations. We have mapped a very clear north-south plains. We, through surface fault mapping, we have seen the same thing. And there is nothing on the surface that suggests that an east-west significant earthquake that would then rupture to the surface has ever happened.
Yeah.
And yeah.
Yeah, I'll invite Martha Savage if you could unmute yourself, because I see that you have other comments down the chat box to explain a bit.
Oh, yeah, I was just thinking that if you're going to be doing a physics-based model, you should put some kind of possibility. It might be small, but I would think that you would want to take a possibility that that could happen. I mean, with the Kaikoura earthquake in New Zealand, basically there were a lot of little faults that got strung together, ended up with magnitude 7.8. And so, that could be, 1991 isn't very long ago. I would, if I were going to be doing a, if it were up to me, I would put in some kind of maybe small probability, but some probability of having a larger earthquake that you.
I see what you mean. We have our catalog here, historical catalog, is about 1,000 years, and we have written in the annals descriptions of earthquakes from the 11th century. And there was never anything there that was indicating anything like that. But if the recurrence time is quite long, then it is easy to incorporate that in a hazard assessment. But then we are completely blind to the probability that we would put to such a fault, to such an occurrence. But I mean, I agree. I mean, we of course we have a limited view of the actual history of earthquakes here, but this is not the only place in the world that we have bookshelf faulting, but there are not many, and everything. I don't even think there has been a suggestion of this in the literature for this region in the north. Yes, there has been, but
thank you. I'm just a little bit aware of the time, but we're having a really fantastic conversation. So I invite everyone to stay along, and we'll go through all the questions, and hopefully, Benedikt, you can spend a bit more your time to answer the questions. But if people have to leave, that's fine. We'll try to answer the questions, and we'll upload the video anyway. So, but please stay on. This is our last.
I know that you. I know that you have time limitations. It's evening here, so I'm relatively relaxed. But you just tell me how you want to do it.
Thank you. I know it's quite late for your case, but we have fantastic questions coming on. So I'll jump to the next question from Sopko. So he's asking, how quickly do ground motions attenuate in Iceland compared to with some tectonically stable areas?
Well, okay, tectonically stable areas are famous for their very, very low attenuation of ground motion, primarily through reflected phases. Basically, what you see in the literature, that the stable areas are on this end and Iceland is on the other, and everything else is in between. There are only maybe a couple of subzones of Italy that have similarly fast, not as fast attenuation of ground motions here, but even California has very slow attenuation compared to us. So yeah, I don't have the numbers in mind, but I studied this at one point when I was in the US, the attenuation in Eastern North America. And, but I don't have the plots, but there's a striking distance between them.
Yeah. Thank you. So we have a question from Luke, and he thanks you for your latter point on the usefulness of certain data in earthquake early warning is important. He says,
Yeah.
it seems that the reliance on present seismic system is somewhat blinkered approach. Have you considered any other sensor data? And I don't know, Luke, if you want to explain a little bit what you mean by a blinkered approach, if you're still online.
What's a blinkered approach, if I may ask?
Yeah, thanks, Marion, and thanks, Benedikt. By blinkered, I'm sorry, it was more just an inquiry rather than a criticism.
No, it's fine.
I look at these systems which rely effectively on an earthquake having to happen before there's any warning that can be given. And so that was very important what you said, that clearly to some people an early warning system is of no use because they're simply too close. What interests me, and I had this discussion with Raj right at the outset, is any way of predicting or at least giving some probability of an earthquake some hours beforehand or minutes beforehand rather than seconds.
Yeah.
Which to my mind would rule out the sort of present seismic sensors and things that tend to be used.
Yeah.
And so I was just interested to know whether you had considered or knew of anybody else that had considered any other sensor data, and one of the sort of ones that seem obvious to me is geomagnetics. And so that was really the question.
I agree.
Was, you know.
I agree. I think the problem with us specialists is that we are specialists. We are very good at explaining what we are specialists in, but when we are asked to enunciate what we think it all means, we are out of our depth. The only way for us to make any headway is to have a large consortium of different specialists in different fields. And that includes what you said. And I actually ended up here. This is what we can do now. It's within our realm, and that goes a long way to move the needle towards the risk mitigation. But for the future, at the birth of earthquake engineering in Lomnitz's and Rosenbluth's book, they said for an earthquake prediction to happen, you need where, when, and how large. And if you cannot say all of those three things simultaneously with practically feasible uncertainties, you should not say anything. Now, it doesn't mean that we don't think about it. And from my experience here in Iceland is that when we have something happens, when we see a geophysical marker is moving, we go around, we talk to the hydrologists, the tremor people, the geochemical people, the geomagnetic people, those are monitoring the strain, those are interpreting INSAR and real-time GNSS. And we go basically over the entire group to ask, is any of your markers moving also that might give us a clue to what is happening? And that includes the multiple other sensors. So I think the easiest way, because we cannot rely on it, we have to have a system in place where we're monitoring all these different geophysical markers in real time and have on the screen at our institute just all the time on record. And then when something happens, we need to go back and learn from it and see what markers started to behave. What is the correlation between the different markers? Are some of them at the similar time starting to act out? And that is our best clue towards what I think you were referring to. It would be best if we could actually get closer to an operational earthquake forecasting in a shorter and shorter time window.
Thank you, Benedikt. I guess feel if anyone has a question, raise your hand, but I'll go to the final question from the chat box. And this is relating to risk mitigation. So you mentioned that practically it's between that 5 to 10 seconds that is, quite useful. But how about using automated system? So how about using the warning to minimize risk through automation, reducing the risk within infrastructure or due to infrastructure? Yeah,
that is the only way. But for that, and that's where I think that's where we need a decision support system based on any of the algorithms through comparison of the algorithms. And the decision support system needs to consider the uncertainties as well. Because if we develop an automatic system that basically has a screen at the stakeholders' place that goes red if something is supposed to happen. If we don't include any measure of uncertainty, or if we just give them something that blinks, then they take that at absolute value, and all of a sudden we are responsible if we are wrong or if something goes wrong. So what the biggest service that we as geoscientists, as engineers, as just practically thinking people, is to be honest about what we don't know. We can say this is our best estimate, but here's the probability function. And so it is 68% likely that it happens in this range. And in this range of these values that you are interested in. Now, this range, does that have any meaning for you? Can you make decisions based on this range that we give you that actually can improve your reliability of operations? If the answer is yes, then we're in business. But we need to be honest with the uncertainties and the range of values that we may actually get out of our systems.
Thank you. Thank you.
Answer that.
So does anyone have any other questions that you want to ask Benedikt? Okay, Chandrajan.
Yeah. Hi, Benedikt. Thanks for your great session. So I got lots of knowledge regarding the earthquake early warning implemented in Iceland. So I have a question. So we are also trying to implement earthquake early warning using the Raspberry Pi 4D at our lab. So I'm just wondering so when I was working with the Raspberry Pi 4D sensors, I am having lots of noise with the sensor. So what are the techniques we are using to tackle the noise in the low-cost sensors? Because comparing with the high-end sensors, there are a lot of noise in the low-cost sensors.
You're talking about acceleration time histories, for example.
Yeah.
Now, my question is, do you need it? The resolution they will give you very low accelerations. They have sensitivities that are well below what we feel. So the way I look at it is that the system, and this I found when I was working with Hamish and when we were developing the prototype for a system that was cutting out all those low amplitude signals that came from an urban environment and were triggering the system. We basically had a condition, and we published a paper on it, where we say, we don't look at any data from the instruments. We don't even consider the time histories unless 2 or 3 or more instruments, they all triggered within the same short time window, which is then designed based on the size of your network and how close the instruments are, because anything else is a transient. So what we did then, we then, our data box filled then with data, and that was tested in the magnitude 6.3 earthquake here in 2008. Our data box was filled then with data files of actual earthquake ground motions. But all of the other stuff that was associated to some noise was just, we never looked at it. But the fact that they are not sensitive enough is irrelevant. You only need them to be very sensitive if you want to test your systems when you don't have any data coming in. But in the end, practically speaking, you only need the instruments to be sensitive to trigger above the strong motion threshold, let's say 3 to 5% G, because it's vastly more than that in the instruments that are close to the earthquake fault, if it's a significant earthquake. And if it's not, then it doesn't affect anyone. So this thing works even if the instruments cannot even record lower than 3% G, but they record much lower than that. So don't have any issues with that.
Thank you, Benedikt.
Thanks,
And thank you for everyone for your questions as well. And as you can see, it's ranging different types of questions from different, I guess, disciplines from our audience. And yeah, just a lot of thank yous in the chat box for your presentation and for gamely answering all their questions, really. So I think we'll probably have to wrap up now. But just first, really want to thank everyone for your participation through 2021, for all the webinars that we've had, and especially today with all your questions. And what I find it really, we really enjoy hosting these sessions because everyone's really game to ask their questions, and our speakers such as Benedikt have a really great conversations and discussions. So thanks everyone for your participation, and we'll continue to do this next year. So keep in touch and hope everyone have a good holiday. But before I just wrap up, really just want to thank Benedikt, but also give a chance for Raj to say something from CRISiSLab.
Thanks, Alicia. Thanks, Marian and Alicia. So thank you very much, Benedikt. And it's, I think, great way to end the year. So thank you so much for taking time to do that great presentation, which is really, so relevant for us as well, because we are using Raspberry Shake extensively. So very quickly, I think I should kind of, when we look back, we started this 2 years back. So we are coming into the end of our second year. So it has been quite challenging 2 years for most of us. But despite that, I think we learn a lot as a research group. I think this platform has given us opportunity to share that knowledge among us, hopefully help everyone who's kind of interested in exploring about earthquake early warning related things. So I must thank our funders. That's really, really important. Without them, we are not going to have these sessions. So especially the Earthquake Commission, as well as Massey University for helping us. And so it is actually for a window of time. So so we'll have to find new opportunities to continue this work, and we are quite passionate to do that. Whether we get the funding or not, probably supported by our research center. So as Marian said, we are really planning to bring more speakers to give opportunity for all of us to get that knowledge and share our knowledge. And other really important thing we are looking at next year, I think we have listened to a lot of experts and gained a lot of knowledge, but we haven't given opportunity to that two-way communication as such, right? So we want to create that platform where we have that conversations, ongoing conversations, not only people come and listen to these sessions, but have kind of ongoing conversations, building their networks through these kind of monthly sessions. So I should thank the team, research team as well. We have a great team of researchers here, and hopefully we'll be engaging with expertise across the globe in the coming years. And special thanks to Marian and Alicia, keeping us all together and organizing all these things and putting a lot of effort. So thank you, everyone, and have a great Christmas and enjoy the next year. Hopefully we'll have pandemic free, or I don't know, new world coming in the next couple of years, or probably, I don't know. But I think we have built quite a big resilience last couple of years. Hopefully we should be all right.
Thank you very much, Raj.
Yeah, thank you for that. And thank you for having me. It was a pleasure, and I really welcome the New Zealand connection, continuing that. I wanted a good thing that you mentioned about the two-way communication, because there are probably some questions left, and maybe I did not address fully some of the questions or what people were meaning. So I would like to invite, if if people can contact me on a two-way communication freely, I would be happy to. And I think what you've been doing here with this webinar and your efforts is really something to be an example for others. And the way you approach it, you're doing it in such a way that I'm very, although I don't know anything about it, but I think I'm optimistic with regards to future funding or future projects that you are planning. So very well done. Thank you.
Thank you very much, Benedikt. And we forgot to acknowledge that it's actually 10 o'clock for Benedikt at night. So thank you very much.
Now, yeah.
And are you ready to go to bed later? Yeah.
That's fine.
Yeah, last time it was Benedikt in the morning, and he was drinking coffee while discussing this opportunity with us. So it's very lovely, very tricky time zone. So thank you very much for attending this session this year. And so actually next year, we already have our next speaker lining up. So she will be Elizabeth Reddy from United States. So she will be sharing the situation of community practice in United States. So which aligns what Raj just said. We will have a more concrete plan after her session. So thank you very much, Dr. Benedikt Halldórsson, and we will wish everyone a happy new year and see you next year.
Bye-bye. Thank you very much.
I will be sharing this recording, and with, if you may, I will share your email along with everyone.
Sure.
Cool.
No problem.
See you. Bye.
All right. Bye-bye. Thank you.